Hi, welcome to another lab uh, for Nanophotonics course. So today we're going to be looking at the S4 Stanford's S-matrix based uh, transmission calculator. We're going to be trying to uh, gather the results for this paper. In this paper, a wave is sent towards these nanogrids, nanowires of gold. The gold is sitting on top of an ITO layer, indium thin oxide, and there is quartz at the backside. Of course, the light is coming from air. We are going to be investigating the TM case, in which the electric field will be perpendicular to the grids, so that it will be transmitted. The wave will be transmitted. If we look at the schematic here in this case, we have this this wave along this direction perpendicular to the wires that is expected to be transmitted, whereas the other one is not. Okay, so if you use the link that I gave you, you will end up on this website, and we'll come back to these documentations later on. You'll have to click this launch tool button. Yeah, sometimes it might say you have too many things running, so let's kill one of these. All right, so it will take a little while for it to get ready. Okay, so this is how it's gonna look like once it's ready. We'll first in this lab use the graphical interface. So there is also the option of using the S4 input tag, but we'll not touch that yet. So graphical interface, parameters. Okay, so as I told you, the structure is going to look like this. So we have air, gold nanowires, ITO, and quartz at the back. So we'll have to tell that to the simulation tool. The first layer is going to, we have to, in this part, we have to select how many different materials we're going to be using. So as I told, it's going to be vacuum, gold, ITO, and quartz. So that adds up to 4 different materials. The first one is going to be vacuum. The second one is going to be gold. So metal is correct choice, but then you have to come here and select gold. As for the third material, we will have to choose indium thin oxide. And the fourth one, we will have to enter that manually. For quartz, let's enter a real part of the electric function as 2.14, and it's going to be lossless, so 0 for the imaginary part. Okay, so we have entered vacuum, metal, gold, indium tin oxide, and as the final thing, we've also entered the real part of the quartz. All right, so now the second thing is to go to this layers tab, because we're gonna have to explain our structures now. The materials are selected. Here, it asks us to choose the base vectors. This is basically asking you to choose the dimensions of the dx and dy. Okay, so our problem is actually if you look at it, a one-dimensional problem. So we have alternating periodic grids altered by dx amount, and for the first run we'll assign that dx number, the separation between the grids, to be 350 nanometers. Be careful with the dimensions, of course, 350 nanometers. Okay, so y, on the other hand, is going to be 0 because this is a one-dimensional problem. We don't have the periodicity along y-axis. So y-axis is this axis. So I have infinitely extending layers there. So correspondingly, my second y-axis will also be 0. And my other base vector will be 0. So this is going to take a unit cell from 0 to 350 nanometers along x, basically. And that will be applied to each one of these materials and the layers. So select the number of layers. So we're talking about the first layer right now. We will not activate any of that. Okay. So semi-infinite top layer, that is our vacuum. So that is material 1. If you go back to the materials tab, you can revisit and try to remember what the associated number was for each material. So it's material 1 for vacuum, and it asks us copy the semi-infinite layer as bottom layer. No, you will not copy that because at the back we have quartz. If we had air at the back too, we would be able to copy that. Get the Poynting flux. Yes, we will get the Poynting flux to determine the reflection for the vacuum. All right, and let's also do the semi-infinite bottom layer. So as I told you, that's going to be quartz. So let's choose our quartz layer, layer 4. We will also get the Poynting flux. That's going to be the reflection, the transmission. By the way, it's getting it from the immediate exit side also here too, so you don't have to touch any of that. All right, so semi-infinite layers are done. Now coming to the layer 1, that is still vacuum layer. So thickness of the layer, it could be 100 nanometers, should not really change with the assignment here. You can check it actually, I haven't done that, but it is set to be material 1 vacuum. And I don't have a pattern in this case for the vacuum yet. So everything is good here. Now scroll up and select the second layer. So this is going to be the second layer. Again, the base vector will be 350. All the things are the same so far. We'll come here for the second layer. Okay, so this is going to be the layer where we define the grating structures, the nanowires. We will do the following trick. We will assign the bulk layer to be, by the way, in the paper, their thickness is given to be 20 nanometers, but I guess we will take it 15 nanometers this time. So thickness of the layer is going to be 15 nanometers. And the material type will be vacuum. So you might be asking why. It will become apparent in a second. We will assign a pattern here. So we'll put a bulk block of vacuum, and we will add a pattern into this. So we'll carve out a portion of the vacuum and replace it with our gold. So select the shape of the pattern. It's going to be rectangular, of course. Select the material. Yes, so this is how we insert gold material into vacuum of 15 nanometer thickness. Okay, so this is asking me center of uh, the nanowire. It can be at 0, 0, and angle. So tilted or not, it's not tilted, so it's 0. The nanowires are not tilted. The half width of the pattern. So be careful with the dimensions. It's given to be nanometers. So half width is in the paper given to be 15 and 100 nanometers is the full size. So 50 nanometer will be the half width, and it is extending on the other side, so it's 0. Okay, so we got everything set here for the layer 2. Now let's jump to layer 3. Layer 3, that layer is going to be also 15 nanometers. So you can check. I don't know what will happen if we don't write units here. But we have to be careful, I guess, with the units. The material will be material 3, ITO. I don't have a pattern here. It's just a bulk material. Okay, so, and as for the fourth layer, let's assign another 100 nanometer thickness for this one, just like we did for layer 1. And it's going to be material 4. That is the quartz we manually entered. We don't have a pattern here too, so that's again 0. Okay, so all these settings are done. We defined the geometry now. We have the materials associated. Now the simulation parameters. Okay, so here, we'll talk in the end a little bit more in depth about this, but maybe it might be a better idea to leave this discussion for the photonic crystals. But for the periodic structures, you have to have a certain number of plane waves associated in your symmetrical structure. For that reason, we will use 49. So instead of the scroll, I'll just enter 49 here. So that sets the plane wave components to be 49 inside the symmetrical structure. The plane wave is coming at a 0-degree angle normal. Normal incidence. The S wave, which is the TE wave, is 0. We're not interested in that. We're interested in the P wave. That is going to be 1. These two entries are giving the phase, the relative phase of the waves. We're just going to leave them as 0. Okay, so here this is the place where we define the units of the frequency on the axis, of course. So we're just going to set that to be 1, meaning that the frequency will be given as c over speed of light over nanometers. And we are asked to enter the wavelength range. So if you go back to the paper, the results are collected from for photon energy of 1.5 to 2.4. So EV to nanometer. I very much like this place just for quick conversions. So 1.5 electron volts is like 826, and 2.5 on the other hand is 400. So it's like 2.4 is on the other hand this much. So it's like from 500 nanometers up to, we can safely say, 900 nanometers. So let's enter those numbers here. From 500 nanometers to, actually that's not a bad number, just let's round it up. And the step size, let's enter 1 for that. Okay, it has a lot of smoothing. The software is doing a lot of smoothing and making results much more um, realistic instead of sudden spikes in the results. So smoothing range, let's set that to 5 nanometers. Okay, so looks like we have everything set, and we will get the reflection and the transmission from these two Poynting vectors flux. Okay, so if I didn't skip anything, so now we should be able to get the simulation results. So it's going to convert whatever you entered into a language, the S4, that is the Stanford's software language. We're going to come back to that in another lab. So this is going to take a few minutes. I'm going to pause the video here. Okay, so we got the simulation results. So this one is the transmission result, and this is the reflection result. So what we have is basically, normally we have transmission of the waves through the grid. So the waves at normal incidence are passing through the grids here, but for a certain frequency range, we have the plasmonic resonance of the nanowires coming in, and they are lowering down the transmission basically. Okay, so let's get these data to our computer. I think this allows us, so this button should allow us to do that. The others, yeah, let's hit that button. So that's just the image, but we need the data, of course. So that will just save it to somewhere. Let's open it. Yeah, so it did open it like that. Maybe could be a better idea to actually. Yeah, so I'm opening it with Notepad, the results. So the results are given here. Okay. So that's the transmission. And this is the reflection. These two are critical for us. So let us get our data. I'm just gonna quickly copy it and open my Octal. the MATLAB clone that I had recommended for you. If you go to the desktop and we create a, actually let me do that here. I just created a new text file there, and inside the text file I'm copy pasting the reflection data. Sorry, the transmission data. You have to be careful, of course, which one you grabbed. The transmission data. Okay, so that can be, we can rename that to be transmission. And let's also get the reflection data. And I'm gonna again open a new text file on my desktop, and I'm gonna call it reflection. Okay, those two are saved on the desktop, so I can load the data. As easy as that. Now I can try to visualize what I have here. So for the extinction coefficient, the extinction coefficient is given as minus ln(t) minus ln transmission. So let's try to plot that first. And don't forget that what you're gonna try to plot is the axis should be EV in EV, so electron volts. So that's why I'm dividing the wavelength information, which is in the first column, with I'm dividing 1240 to that value. That is how I convert from wavelength, nanometers wavelength, to EV values. So let's also take the logarithmic of this guy, the transmission. And yeah, so this is how the extinction should look like. So if we come here, for example, it's around 1.8 electron volts as given in the paper. So it should be around 1.8 or 1.9. Yeah, it's selected to be 1.9 here. So this is the plot we're looking at for 350 nanometers for the TM case. The deviations between our plot and their plot is mainly because of the different choices of the dielectric coefficients. We did not use their gold selection, and also the ITO. We basically did everything with NanoHub's material database. But in the end, it's very similar. And we have a very similar plasmon resonance that determines the extinction. So let's so I just entered the X and Y axis by saying EV and extinction coefficient here. So let's save this as one of our figures. And let's try to save it as a PNG file. And let's see if it could. Sorry about this. Yeah, funny enough, but my software, antivirus software, conflicted with the Octal's figure saving option. So I could save the extinction coefficient. I'm going to upload it there to the website too. Let's also do the following. Let's try to see terms of the EV values again. Reflection minus transmission should give us the absorption inside. So the absorption should mainly come from the plasmonic resonance. So let's see. Okay. Yeah. So this absorption taking place at, again, 180 around 1.8, 1.78. Yeah. EV is the absorption that is coming from the separate isolated plasmonic resonance of the nanowires. So I'm gonna call it X label as EV, Y label as, this time let's call it absorption. And let's save this figure as well. So I had to silence my antivirus program for 10 minutes for this. This is absorption. That's PNG. Yeah. So it's saved as well. Okay, so that concludes our lab. What I would like you to do is to change the dx coefficients we've been using. Just investigate it further. The dx coefficient can be altered, and if it's made pretty large enough, then we would see transmission occurring as it is shown here. And at like 500 nanometers, it's gonna make this resonance frequency, localized resonance frequency of the plasmons to be really very sharp, much sharper than the sprout response that we get from 350 nanometers when we go to 500 nanometers in terms of the DX. So you can investigate that uh, as a small lab exercise. All right, so this concludes our lab today. I would like to see you in another lab. Thank you.